Okay, Assalamualaikum and very good morning to all. Okay, today we will continue our next lecture, okay, on the automatic control EMC322, okay, lecture number 2, which is on the plotting the root locus, okay, for the passive control system. Okay, so previously I have introduced you some of the what is the root locus all about. Okay, for today we are trying to plotting, okay, the graph, okay, for the passive control system. Okay, so this is the today class, okay, on the Thursday, which is later on after this class you will be given the assignment number 3, and also during this class you will be introduced to the on the how to plot the root locus for the passive control system using the Matlab software. Okay, so as an overview, there will be 3 sections. Okay, the section number 1 is on the graphical representation of the characteristic roots and corresponding solutions. Okay, so basically this has been introduced previously by Dr. Iftisha on how you can determine the stable and the unstable regions of the graph in the S-plane, and also the next one, how you can do a parameter variations by have a different mass, damping and stiffness of the system, that you can plot a different curve of root locus for each of the system. And finally, I will introduce to you on the how you can plot the root locus using the Matlab software. Okay, so this is basically the what you have been introduced previously, okay, on the root locus of the characteristic equations. Okay, so for the free vibration of the single degree of freedom, okay, which is mass spring damper as shown in the figure here. Okay, you have the mass, stiffness and damping, okay, and also the output displacement. Okay, so that you can get this as per equation number 1. Okay, at this stage basically you should already know how to derive it. Okay, you can divide into 2 position, which is on the plus and minus directions, okay, using the equation F equal to ma, so that you can have a total force here, which is on the stiffness and also the damping, which is minus kx equal to and minus cx dot equal to the mass is mx double dot. Okay, so when you bring all together in one side, so that it can have mx double dot plus cx dot plus kx equal to 0. Okay, so but this one we just want to represent it into a y directions, so that it can also can represent as a y lah. Okay, so this is how you can derive very simple equation of motion for this diagram. Okay, and from this you can transform it to the characteristic equation here, okay, using the Laplace transform, so that it can be in the S domains. Okay, so basically this one from these equations, so you know that this is when you move the S, you divide by M, so you get the equation of Cs plus K M equal to 0. Okay, so Cm actually is represented by this. Okay, in previous lecture you already has been introduced the equation for the damping ratio and also the natural frequency. Okay, so this is K over M is actually equal to omega n the power of 2. Okay, which is basically the natural frequency omega n equal to K over M, and the damping ratio here on the C is the damping. You can also represent it as a C equal to 2 damping ratio multiplied by omega n m. Okay, so this will be your equations for the damping ratio and the natural frequency of the system. Okay, so from equation number 2 and 3, basically you can determine the roots, which is the S1 and S2. Okay, using these typical equations that you have been learned in the calculus, which is basically is about from the minus b plus minus b to the power of 2 4ac, which divide by 2a. Okay, this is the a is represented by the mass. Okay, the b is actually the stiffness, the damping, and the c is actually the stiffness. Okay, so it's also you can represent as this form when you transform it to the natural frequency and damping ratio. Okay. Okay, so the next one is okay, this is the important part, which is on the graphical representations. Okay, so previously you already been explained here, but I will want to emphasize this again. Okay, on this one, so we can see here one by one here. Okay, so we open these two so that we can go on to these 6 rules. Okay, the first rule is that the roots, the roots lying further to the left in the S-plane indicate that the corresponding response decay faster than those associated with the root closer to the imaginary axis. Okay, so you can see here, okay, the response at this part is actually decay faster. Okay, so this is the imaginary axis, and this is the real axis. Okay, where imaginary is equal to j omega and real is equal to sigma. Okay, and the equation is s equal to sigma plus j omega lah. Okay, so this is sigma by real and j omega is the imaginary part. Okay, as it's moved the left further, so that you can have a response decay more faster lah, which means that at this area the damping or the damping ratio is the value is high, so that you can reduce the vibration more faster than the part that's close to the imaginary axis here. Okay, that's the rule number 1. The rules number 2, if the roots have the positive real value, okay, of the S plane, the roots will lie on the right half of the S plane, okay, which is on this side. Okay, and the corresponding response grows exponentially and hence it will be unstable. Okay, so that's okay, this is the axis. Okay, and when all the response is on the right side of the graph here, okay, so that the response become unstable like this. This is which is also associated with the resonance phenomena, where the amplitude will increase in time. So it's actually a very dangerous situation. Okay, so we see the roots are the number 3. Okay, the rules number 3, if the roots lie on the imaginary axis, okay, with 0 real value, okay, no real value, the corresponding response will be naturally stable. Okay, as you can see here, when the plot is at this point, okay, the response is actually is naturally stable. There is no increase in amplitude. The amplitude is just maintained, and there's also no reduction in amplitude also. Okay, rules number 4, okay, if the roots of the 0 imaginary parts, okay, the corresponding response will not oscillate lah, okay, which is 0 imaginary part, which means that it's lie on the real axis here. Okay, at this axis, okay, it's lie on this axis, there's no oscillation. Okay, it's directly go to the 0 position. Okay, which means that at this stage is a overdamped. Okay, at this area is underdamped. Okay, so you already learned before this. Okay, and when the damping ratio, okay, is below than 1, and this is when the damping ratio over than 1. Okay, the next one is on the rules number 5. The response of the system will exhibit an oscillation behavior only when the roots have non-zero imaginary part, which means is at this area lah. Okay, at these locations, so they will have a vibration response. This will oscillate. Okay, and the final one is on the larger the imaginary parts of the root, the higher the frequency of oscillation of the corresponding response for the system. Mean that the higher the response here, mean that the frequency will increase in time lah, which is also the omega n will increase in which the value of the higher plot at the imaginary axis. Okay, so that is the rules on the how you can, after you get the plots, okay, of your response, so that you know your system is stable or not. Okay, the next one is on the second part, which is on the parameter variation and root locus representations. Okay, so this is the equation of motion that has been introduced to you previously. Okay, where we have the natural frequency omega n, okay, the damping ratio, okay, the undamped natural frequency. This is undamped natural frequency. This is the damped one, where when the system has a damping elements, so they will have the undamped and also the damped natural frequency. Okay, and this is the period of time that you can determine for the response of the system. Okay, so this is the example of plot how you can interpret the omega n, okay, omega d, the damping ratio, and also the time in the S-plane. Okay, so as we know, this is the imaginary line and this is the real line. Okay, this is the origin 0. Okay, so at the point A, okay, at this stage when the response is in the circle line, so we have the A is actually the value of the natural frequency omega. Okay, and when it move over this line, the natural frequency is maintained the same, because you can see here, okay, the line of omega n is always the same to this movement of the circular part. Okay, the next one is on the omega d. Okay, when the plot is lie on this imaginary part, you can determine actually the value is actually the omega d lah, which is the undamped natural frequency. Like for example, when you have the value of 3i, so that you know that this is the value of omega d. Okay, for example, this you have the value of here, this part. Okay, this is the value of the real and also the imaginary part is equal to omega n value. Okay, so when it moves to here, the point number q, this means that the system is actually critically damped. Okay, where the damping ratio is equal to 1. Okay, it's a critically damped. This is at this line, it will damping ratio over than 1, and at this area the damping ratio is below than 1. This is underdamped. Okay, this is over damped, and this is the critically damped. Okay, so another parameters that you can get is the angle here, the theta, which is sine, the inverse sine of damping ratio. And when you have the plot at the real line, so you can, the value is actually equal to minus damping ratio multiplied by omega n. So as what we have learned in the rules before this, okay, as the plot if move higher to the axis, imaginary axis here, so the omega n will be increased, the frequency will be increased. So that's the omega n2 is basically bigger than omega n1. Okay. Okay, the next one is on the same one. Okay, at this plot you will have the omega d. Okay, so that's the omega d1 is actually larger than omega d2. This is the undampened the dampened natural frequency. Okay, the omega n is the undampened. Okay, this is the dampened one. Okay, so also the theta, okay, when it's moved here and here, the theta will be different, so that you will get a different angle lah. Okay, with the different value of damping ratio. And also goes to time, when it moves to the further to the left, so that the value also will be different. Okay, so this is all the important elements that you have to know, so that you can translate your root locus later on the in terms of value of natural frequency, damping ratio, and so on. And also you can also know that your system is stable or not. Okay, that's the powerful of root locus plot. Okay, so let's see the example on this one. Okay, which is on how you can plot different root locus with a different parameters variation. Okay, so a plot or graph that shows how changes in one of the parameters, for example the mass, stiffness, and damping and stiffness of the system, will modify the roots of the characteristic equation, of course, which is the different value of m, c, and k. This is called characteristic equations. So that's it will be different, and it will also generate a different root locus plot. Okay, so we can have a three condition with different of damping or damping ratio, stiffness, and also the mass. Okay. Okay, let's see the first example here. Okay, on the case study number 1. Okay, this is study of root with the variation of damping, the c value here. Okay. Okay, the question asks you to plot the root locus diagram of the system that governed by the equation by varying the value of c bigger than 0. Okay, so basically from this diagram you already know that we have the mass, spring, and damping system. So from this root equation you already know that the mass equal to 3. There's no the value of c is varies, okay, from 0 to larger value, positive value, and also the k value you have a 27. Okay, this is written here. Okay, for the root of equation you given by this one. Okay, previously you can translate to the roots solution. Okay, so a is equal to the mass here. Okay, and b equal to the damping, so you will determine the damping value here, and also the c is a stiffness. Okay, so you can transform into these equations, so that now you can do a solution. Okay, okay, so let's see how you can plot this. Okay, so see here. Okay, so you know that okay, so the key point is that actually the hint is given by you must determine the c is bigger than 0, right? Okay, so you can start the value which is c equal to 0. Okay, and then the second one you need to determine the value of the natural frequency. Okay, which is you have to use these two equations. Okay, where at the middle point you can find that when the damping ratio is equal to 1, this is critically dampened, so that it will lie at this location lah. Okay, so you have the value of in this situation you have the value of M given, the K is also given, the damping ratio you set as a 1, critically damped, so that you can determine the C value. So in this case, you can get the C value of value is 18 lah. Okay, means that the roots you will get for the S1 and S2 is -3 and -3, so that's both lies on the position. Okay, another one you can take a large value of C, for example hundreds. Okay, so that you can get the value of S1 and S2 is actually -0.2 here. Okay, there's no imaginary part. -0.2 is somewhere here, and -33 is a larger value lah, is somewhere here. Okay, for the value when is equal to 0, so that you have a positive 3 imagery and -3 imagery part. There's no real part, so that you plot here. Okay, so the S1 is basically start from here when C equal to 0. It's moved towards the critically damped here, and further when they increase the value, it will go towards the 0 position. So this is the direction of the S1. Okay, for the direction of S2, it start with the -3 here. Okay, move toward the critically damped and is going to the larger real value here. Okay, so when you get this plot, actually you can interpret it in and you will know that's how the system will react. Okay, so basically the plot is only at this area. Okay, so that your system actually is stable lah. Okay, because of course, because we have a damping. When we include a damping, so that there is no this possible or resonant phenomena will happen lah, because you have a damping that will absorb the vibrations. Okay, so you know this area is a stable and undamped. Okay, when it's going to these positions, okay, it's actually a stable and critically damped. Okay, and let's go to this the points in this line. At the real line is a stable and overdamped. Okay, this is the damping ratio indication. Okay, where this at this area can have a damping ratio of 0, in between 0 and 1, which is actually the damping ratio is below than 1. This the damping ratio is over than 1. Okay, this is damping ratio equal to 1. So basically this, when you have this plot, you can know this is the area of damping ratio below than 1, the underdamped, and this is the overdamped. Okay, also another parameters that you can get. Okay, when you take, for example, you take this point. Okay, you can verify at this area when is maybe the value of for example, the C equal to 8. Okay, you can have a plot S1 here and S2 here. Okay, so you can verify it. Okay, where at this reading value is actually equal to omega d, and when you project the line here is actually equal to minus damping ratio multiplied by omega n. Okay, so there's a lot of parameters information that can be extracted from the root locus. Okay, that is on the for the variation of C value. Okay, where in this at this situation, the omega n is consistent. Okay, because you have a fixed kn and value. Okay, so let's see, the next one is on the how you can vary the parameter of k. Okay, so we use the similar roots equation here. Okay, when we know that m equal to 1, the c equal to 16, and k is to be determined. Okay, so you have these parameters, and you can translate into this roots equation to determine the roots, which is S1 and S2. Okay, so for the variation of k, they will generate a different root locus plot. Okay, you have these roots equations. You have the same one, omega n and damping ratio. Again, you can determine the value of you can start the value plot of 0. Okay, when you get the s, when you replace the k go to 0 here, you can get the plot of s1 start from 0. Okay, and s2 start from minus 16. Okay, so now at this stage you already know the limitation lah. Okay, we will start from here and here. Okay, so the next one, as usual, you can use damping ratio equal to 1 to determine the plot at the critically damped. Okay, you have given the value of C and M so that you can determine the value of K. So from this, you can get the K value is equal to 64, where the plots equal to minus 8 and minus 8. So it will be at this location lah. Okay. So in between, can take any of points so that you can projection where the S1 is moved from 0 towards this point, and S2 start from minus 16 toward this point. Okay, is at this stage is differently from the C, which is over dampened. Okay, because it's lie on the real axis. Okay, then when you go to the larger value of the K, for example, you take the maximum value like this. Okay, you can have a plot here. Okay, like K equal to 1 to 8. Okay, you have plot here lah. And of course, in between value will generate at the in between points on the lines. Okay. Okay, so that's on the plot for the different K value. Okay, again you have also the same lah, the region of how you can indicate the regions here. Okay. Okay, the next one is on the variation of the mass. Okay, so in this equation you have the C value equal to 14, K equal to 20, and mass is to be determined. Okay, so you can also show in this usual equation of roots. Okay, so you have this equation of roots and omega n and also the damping ratio. Again, for this one is you must be alert that the m value cannot start with a 0 value, because when we have the 2a here, okay, we've used set the value of 0, say there will be the error lah. Okay, you for the m you must start with the value of 1. Okay, so by replace the value of 1 here, okay, you can get the s1 is start from minus 1.6 here, and the poles for the s2 start from minus 12 here. Okay, again you replace the value of temperature equal to 1, and the C is given K, and you can get the value of M. So from that you get the value of M actually equal to 2.45, and the value of S1 and S2 is at the minus 2.86, basically at this location. Okay, so the S1 will move here and S2 will move in this direction. Okay, as you increase the value here, okay, to the highest value of 100, for example, you can have a different plot where S1 is moved to this direction and S2 will move to this direction, and both will going towards a 0 position. Okay, you can also take any points here to verify it. Okay, for example, at this location, okay, which you can also get the value of like the omega d and everything lah. Okay, that's how you can plot it. So the hint is take the minimum and maximum value first, then when the damping ratio equal to is a critically damped, and then you can have a most the three important plot of the poles here. Okay, and later on maybe you can take 1 or 2 points in between these regions so that you can have a roughly the 2 points, for example 1 and 2, so that you can roughly sketch it. Okay, okay, that's all for this part, for part number 2. Okay, variation of roads for the study of road for the variation of M, C, and K. So on this final part, let's see how you can plot it in the Matlab to verify your sketching of the root locus. Okay, so for the Matlab control system toolbox provide several useful commands to produce a root locus plot. Okay, and can extract also the important information from them. Okay, so the basic function is a root locus system here. Okay, it's very simple. You have to transform it into transfer function, then you can use as this command. Okay, for example, okay, you need to transform in like the equation number 12. So basically you can refer back to my previous lecture. Actually this is the also represent the roots. Okay, the roots, the characteristic equation of the transfer function. Okay, so where the system is correspond to the transfer function of nd divided by ns divided by ds. Okay, this is the numerator and this is the denominator. Okay, so and the k parameters varies from 0 to large value. The k actually is not represented by the stiffness only, but for the passive system it also can represent as a mass, damping and stiffness, because this is the parameter that we varies. Okay, so the k actually is represent the big k is represent the parameters that to be determined, or we call it a gain. Okay, a gain that can by different the value of gain you can plot a different root locus lah. Okay, and basically the order of the denominator is bigger than numerator lah. Okay, this is example on the example of the transfer function lah. Okay, okay, let's see the example here on the previous one. Okay, you can refer back to the difference c value. Okay, the equation previously, equation number 6, we will try to plot to verify our sketching previously. Okay, we have this equation of roots characteristic, and from this you can rewrite them by using the equation number 12. You can rewrite them in this form. Okay, so you move 3 here, so it's become s power of 2 c divided by 3s, and 27 divided by 3 is equal to 9. Okay, so from this you know that this is the k parameters. Okay, so that you can rearrange it. Okay, by take the gain parameters alone here. Okay, and everything is considered as a denominator, as the power of 2 plus 9 will be moved as this in the blue color. Okay, let's be the parameters, the gain that we want to tune as the standalone parameters. Okay, so that will be easier for you to determine it. Okay, so we know that now we have the ds equal to s power of 2 plus 9, the k c divided by 3. Okay, this is the gain. Okay, and the ns is just s lah. Okay, and the pose, actually you can using the Matlab you can determine the pose is s equal to plus minus 3i, and 0 is s equal to 0 lah, because there is no part on the above. Okay, so let's try this. Okay, okay, so this is actually your transfer function lah. Okay, as you can see here. Okay, so you have the transfer function is numerator divided by denominator, so that you have at the above is actually s 0, because you need to represent because it is in the transfer function we arrange it by order. For example, s power of 3, s power of 2, s, and the numbers lah is 1 or 0. For this case you all just have the s value, which is for the final one. For the k there is no value, so you consider as 0. Then for the order at the numerator you have the s power of 2. Okay, which is actually 1. Okay, and there's no s here, and the final one is 9. So in the transformation you can present as 1, 0, 9. Okay, and the above you can represent as a 1 0. Okay, so this is what you have to write in your codes. Okay, the above one, the NS, and the below one is a DS. Okay, so actually NS is expressed as 1 0 since actually the NS is equal to S plus 0 as explained before. Okay, so then you have all the system, and then you can have this command to get this locus plot. Okay, uh, okay, let's try it. Okay, let's verify it together. Okay, you can open your Matlab. Okay, and then you can write your system here. Okay, so actually I have written here, so I just recall back my codes. Okay, so okay, so this is has been written here. Okay, the system transfer function, okay, 1 0, the numerator and denominator is 109. So when you enter it, it will represent shows you your transfer function lah. Okay, which is S, the 0 is not written, and S power of 2 plus 9. Okay, so you can verify it here. Okay, the numerator is uh, S the power of 2 plus 9, and numerator is S only. Okay, so from this actually you can know how to generate the zeros part, the above part. Okay, for example 0 here, so you know that 0 is equal to 0 lah. Okay, and for the poles, okay, you can have poles, okay, which is will be given as a plus minus 3 imagery. So you can verify this, the value lah is correct. Okay, so the next one is you just to plot the root locus lah. Okay, you recall the command root locus. Okay, system as is equal, so you enter it, it will generate this plot. Okay, so this is later on you can verify back with your sketching. Okay, from this the good of using the Matlab, you can automatically uh, tap the information from the graph. For example, this point, okay, can get is again 0. Okay, this C equal to 0. Okay, still remember that at the imaginary line there's no C value. Okay, and the pole is plus 3 imagery, there is no value of real, and you can have a natural frequency of 3. Okay, so as going to the critically damped here, okay, you can get the value of gain is equal to 6. Okay, because in these equations C you determine is previously 18 divided by 3 is equal to 6. Okay, and the damping equal to 1 is critically damped. Okay, it's critically damped here. Okay, at this stage we write as 18 because in this equation is divided by 3, so in the root locus plot is shows as a 6. Okay, so also the natural frequency equal to 3. Also you can have verify other points also like this. You just click it, it will give you what is the value of gain, the value of C. Okay, and so on. Okay, so that's the powerful of using this root locus plot, so that you can know your system is stable or not. Okay, and also you can generate a lot of information from there. Okay, so I think that's all for the today class. Okay, I hope you learned something. Okay, thank you very much.